Hi everyone. Good morning, good night, good afternoon, good evening, depending wherever you are staying and whenever you are listening this recording. So yes, today this is Avirup Basu, and today I'll be speaking on autonomous navigation in unmanned ground vehicles. So basically, I'll be covering more on the brief aspect of what are the possibilities of autonomous navigation in UGVs, both in known and unknown environments. I will also cover some of the topics related to maze solving and micro mouse. And then I will also cover some topics related to PID controller, autonomous navigation, and related to the total of autonomous navigation. Before I begin, I had to pay my sincere thanks to uh, the Be My App team and the Intel Software Innovator team for making this conference possible. Thanks to Justin and Grace for giving us the opportunity to speak over here. Okay, yes, I'll just hide this notification bar. So, yes, brief introduction about myself. Currently, I'm working as an IoT application developer at a company called Prestriver 360, which is based in US, although I'm located in India. And I'm also Intel software innovator, mainly in the field of IoT, robotics, and embedded systems, machine learning. I am an active independent researcher. I have published 3 research papers, out of which one is of IEEE, and I've also published a book, Intel System Projects. This book was published and written much before when Intel decided to stop rolling on the boards. So anyway, but this book will guide you through all the basic aspects of IoT using Node.js, Python. So it's kind of a common book. It can be used on any board. So that's my agenda for today. I will have a brief talk about autonomous robotics and unmanned ground vehicles. Then I will talk about what we mean by known and unknown environments. We'll also see about the micro mouse and the maze solving problem, which is pretty much a very big common problem statement in the field of autonomous navigation. We'll also talk about the PID controller, and then we'll move forward with the autonomous cars or self-driving cars. And ultimately, we'll end this entire webinar with a project discussion of where I have actually accomplished autonomous navigation is nothing but just ultrasonic sensors. Okay, so what are autonomous robots? We keep talking about robotics. However, broadly speaking, there are two broad categories of robotics. One is the autonomous side of it, and another is the manual side of it. However, if you want to speak truly on autonomous, then perhaps the industrial robots, as the one shown in the picture, that's QCar robotics, which are usually deployed in the assembly line of cars, can be referred to as autonomous robot. However, there are other robotic systems like Honda's SEMO or humanoid robots, or any kind of robot which doesn't require human intervention can be considered as autonomous robot. So, talking about which the capabilities required for a robot to fall under the category of autonomous robotics are the robot should be task specific with a high degree of autonomy. By this I mean when you are deploying the robot at a real-time scenario or a real-time problem, then there should be as least amount of human intervention as possible. It's not like you are deploying an unmanned ground vehicle and you are controlling the vehicle from a far over distance. Then we cannot consider that as autonomous robotics. That will fall into manual category. And the key factor is that it has to be dynamic in nature in dealing with real-time systems. Now, the second point holds a key value in the case of industrial robotics. So what happens in the case of industrial robotics is that all industrial robots are totally based on real-time systems. By industrial robots, I mean which are deployed on the assembly line of car manufacturing or more on the assembly line sector of it. So it should be dynamic in dealing with the real-time system. Like it should get the real-time value from the sensor or from the assembly conveyor belt, process those data, and again perform some kind of operation as the one which this robot is performing, a kind of welding job mostly. as it seems from the picture. So anyway, so it should be capable of handling like real-time systems. And also, like, the robot should be quite capable in operating both known and unknown environments. The robot should be designed in such a way such that by the use of sensors or by the use of like some kind of sensing equipment, it should be able to sense the environment uh, like where the robot is associated, and adapt itself to the environment. That requires a high degree of autonomy, and that usually falls into the category of autonomous robotics. Then we can speak of like handle intruders without any kind of human intervention. These kind of robots are especially in total real-time systems where the robot needs to handle lots of interrupts. Suppose a robot is, let's leave aside a robot. Suppose a self-driving car. So what happens is that in a self-driving car, you have to handle a lot of parameters in a single moment of time. Something like process of some hundreds and thousands of parameters. So at any stage, the robot may need like to handle some kind of typical interrupts. Like suppose you're traveling at a speed of, let's say, 100 miles per hour, and suddenly some kind of object or probably some person is crossing the road, and at that particular moment need to handle the real-time interrupts without any kind of human intervention. So that would be a typical case of autonomous robotics. Some typical examples will be of the industrial robots in assembly line. KUKA is a very good example of that. Autonomous vehicles, each and every autonomous vehicles, which includes that of air, like unmanned aerial vehicle, something like a submersible vehicle, or unmanned ground vehicle, and even the satellites. Yes, satellites. What happens in the case of satellites and space shuttles or spaceships is that like we program the spaceship or the spacecraft to follow a particular trajectory, and there are certain instances of time in a spacecraft when the spacecraft operates along with itself. There are no human intervention in case of in those cases. And another example would be the autonomous humanoid robots, perhaps a new celebrity robot, Sophia, which recently got the citizenship at Saudi Arabia. Probably that will fall. That will be the perfect example of autonomous robot. And then there is Honda's Asimo. So that is also another very good example of autonomous humanoid robot. And then we come to the like the very huge topic of micro mouse or the maze solver robots. So those are also typically autonomous robots. So anything which doesn't require a human intervention we will be calling as autonomous robot. And now we'll come to autonomous or like unmanned ground vehicles, UGVs. Yes, it may or may not be autonomous. Or not all unmanned ground vehicles are autonomous in nature. For example, the ground vehicles which are used in the military, like the DRDO ducks. So these vehicles are not autonomous. So they are remotely controlled by a operator, like from a large distance away. So it may or may not be autonomous considering ground vehicles. Yeah, it is widely used in the military. And talking about which, the ground vehicles are anything like these vehicles are either remotely controlled or autonomous in nature, and are widely used in specific use cases like military usage. Yes, the army uses lots and lots of unmanned vehicles. I mean unmanned ground vehicles. Then there is the topic of surveillance and reconnaissance. So this type of surveillance and reconnaissance robots can be used in case of natural disasters. Typical example will be the case of the Japan earthquake in 2011. So what happened in that Fukushima nuclear reactor power plant? Robots were used to clean up certain waste, and that is a typical use case of unmanned ground vehicles. Then deliveries. Well, that's a kind of a new topic of that. Although unmanned aerial vehicles are more suited to deliveries, but unmanned ground vehicles may also somehow carry this job of delivering items to the customer. And then the main topic comes in the picture, where it is autonomous cars, which are totally autonomous in nature. And these cars like kind of, so these are all unmanned ground vehicles. Although autonomous car cannot be typically considered unmanned because there's always a person sitting, otherwise there's no definition of car. But still, like we can make it fall into some kind of ground vehicle. Right now we'll move towards the micro mouse, the maze solver robot. This the image which you're seeing is a Pololo 3 Pi robot. It's widely used in the maze solving competitions, and I will discuss about this robot in later part of the presentation. But as of now, we are concentrating on the maze solving aspect of autonomous navigation. So this micro mouse robot or maze solving, typically the terminology micro mouse refers to small maze solving robots. Now this maze solving can either be a kind of like a line maze or a normal maze. By normal maze I mean walls on both sides and there's a path in between, that we may refer to as a normal maze or a line maze. Here we are going to talk about line mazes only. So now right now we'll just discuss about the problem, the concept and the problem analysis, and we'll have a look on the suitable hardware, and then we'll move forward to the algorithm of micromouse robot. This I have just made a very simple track but as the simplest one. So the main concept behind a maze solver is that a robot needs to travel from point A to point B in the shortest possible path. If you just have a look in the picture on the right hand side of the slide, then you will see that there are lots of intersections and there are lots of false paths that leads to dead ends. So the robot needs to handle all these parameters and traverse from point A to point B in the shortest possible way. Now let's have a look at the possible algorithms. So there are, specifically speaking, there are three types of algorithms, like a breadth first search, depth first search, and distance algorithm. The first two are mainly for traversing the maze from one point to another, while the last one, the distance algorithm, is used to find out the shortest path. So what happens in case of a breadth first search is that, like, it's a simple traversing algorithm where you start traversing from a selected node, let's say point A in this case, and traverse the graph layer wise, like one node followed by each of the child nodes, and then the child nodes of those child nodes. So it will be like it's totally like layer wise. You'll be exploring the entire graph layer wise, and then it'll move to the next level neighbor nodes. Although breadth first search is not widely used in the, I mean, it's not at all, I won't say not at all, it's not commonly used in the typical maze solving example. In those cases, we go for a depth first search algorithm. So what happens, like in depth first search, it will take one parent node and then explore its immediate child node and then follow the entire process recursively and ultimately backtrack the way to the parent node. So it involves a kind of exhaustive search of all the nodes by going ahead, and if possible, else by backtracking, it will shift to the other node. So from the depth first search and the breadth first search, we plot a weighted graph, or you can say a weighted matrix, and then we apply the distance algorithm to find out the shortest possible path in that weighted graph. So ultimately, what we end up is like, in case of typical maze solver, normally there are three runs. The first run is to traverse the entire path. The second run is to calculate the shortest path and to move through the shortest path till the end point. While the third one is like, if things go wrong in the second or first case, then you will always have an extra option to go. That's the possible algorithm section of it, and there's not much. You can even just have a look over details of the time complexities and all those stuffs in the of breadth first and depth first. These are pretty much common topics. But what comes again? This is one of the major issue, because what we learned initially, we just simulate all these algorithms in a kind of a simulated environment where we not much care about the hardware. However, a problem will pop up when you are dealing with the hardware. So yes, when dealing with the kind of a line maze, suppose the one which is showed in this slide, in this type of mazes, we normally go for the line array sensor. The image which you're seeing in red color. So this is a typical line sensor array of around eight infrared sensors. So what happens is that like these sensors are digital sensors and they return a digital value, and it's kind of easier to process this data when you are solving for maze, because uh, this like when you are considering a sensor, there are two major points that you need to take care. The first is the whether it's a digital sensor or an analog sensor. That's one of the major point. The second point that you need to take care is like the amount of noise we are getting when there's a shift between the black line and the white line, or the white line and the black line. The noise has to be taken care of, because when you are dealing with a normal maze, by normal maze again I'm referring to the normal walls on both sides and path in between mazes. And in those times, you need to use proximity sensors. Now, these proximity sensors are exceptionally noisy, which I have faced personally. I have used an ultrasonic sensor for my project, and yes, it took me a hard time to figure out how to cancel out the noise. But low noise, low noise sensors also available. In that case, you need to go for infrared sensors. But usually speaking, ultrasonic sensors are a lot more noisy. So generally, don't recommend using it. But if you know how to handle a ultrasonic sensor with all the noise and stuff, then you'll be able to handle each and every sensors. That's a kind of experience that I have gathered. So the third point, the mobility. That is for the robot to move, motors with encoders are used. Now, here is a very important concept of encoders. What does an encoder does is like it calculates the distance traveled by the robot. Basically it calculates the RPM, and by simple formula we can just figure out how much distance the robot has traversed. So again, I'll head back to the myth solver. So why do we exactly require the concept of motors with encoders? The reason is pretty much simple. We need to calculate the distance between each nodes, because at the end of the day we are calculating a weighted graph. So to calculate to calculate the distance between each node, we go for motors with encoders, which calculates the distance in between. So that's the main reason why we go opt for motors with encoders. I'll handle the question for Rishabh. What can be possible data structure to remember the path while backtracking? Well, in this case, I will suggest like we can go for queue. Stack can also be an option, but it totally depends on which algorithm you are following, like if it's a BFS or DFS. Yes, this is one of the most important slides, because you need to filter sensor data, right? So filtering out the sensor data is again a kind of a it's a very heavy task. You need to, and it involves a lot of calculations. So when you're dealing with sensors, proximity sensors, especially ultrasonic sensors, then you need to design a filter. Well, it might be a low pass filter, it might be a high pass filter, or it might be a band pass filter. Now you need to calculate the threshold values of the low pass filter, high pass filter, and band pass filter separately, because each sensor has a different range of value, and that's the reason you need to select a proper suitable threshold of value. So again, this filtering of sensor data can happen in two domains, either in the time domain or in the frequency domain. Now, if you want to operate in the frequency domain, then you need to opt for Fourier transform, which may increase the computational power. But if you can compromise on the computational power, then you can go for Fourier transform. So and it's kind of easier to process the data received by the sensor using Fourier transform. Moving along, the algorithm. I'll just discuss about what can be the possible workflow, not exactly workflow, the possible outcome of the robot traveling from point A to B. I didn't mention point A to B over here, but it's the point A is on extreme left, down left corner, and the point B is this this vertex. Okay. So what happens is that either you need to follow a single route, either a left-hand route or a right-hand route. By left-hand rule, I refer to that when a robot is traveling from point A to point B, it may come across an intersection. Now, the robot will give priority to the left-hand path if there are more than one path, because we are following the left-hand rule. So, let's say that a robot comes from point A to the first intersection. If we didn't follow a left-hand rule, then it would have gone straight and encountered a dead end. However, we are following a left-hand, so the robot will take a left-hand turn, go straight, and again take a left-hand turn, and it will come across a dead end. Now it will take an U-turn, go back, and again take a left-hand turn, and the same process will be followed until it reaches point B. The right-hand rule can also be followed. That is also totally fine. There are no issues with it, but you need to follow at least one rule, because you need to give priority to which side the robot, which side will be important, the left hand side or the right hand side. So that's one part of the story. And second part of the story is like handling dead ends. Yes, you need to handle dead ends, because there will be times actually like half of the time the robot will be like staggering around some kind of a dead end because of the design of the maze. It totally depends on the design of the maze. So when the robot moves, like encounters the dead end, what it needs to do is like take a exactly 360-degree U-turn and return to the previous, that is a previous node, or yes, a previous node. So that also need to handle for handling dead ends, and then you need to apply the your algorithm like a BFS or TFS, and to traverse the entire maze, and finally you apply the distance algorithm to find the shortest path. That's the typical case of the entire maze solving. So just I will have a quick recap of the maze solving, and then I will move forward with the possible control mechanism. So in case of a typical maze solver, what we initially do is like we traverse the entire path from point A to point B, and then what we do, we traverse the path either by BFS or DFS, and then we construct a weighted graph, of the entire robot. Of the entire map or of the entire maze, whatever you call it. And then ultimately, what we do is that we apply the distance algorithm to find the shortest path. So that's the entire concept of the maze solving robot. You can like take different sensors in the picture, line, proximity, encoders, etc., etc. Also, filtering is another important aspect of which filters. If you're handling robotics, if you're handling with sensors, this is the most common thing that you need to handle first. So yes, we have talked about sensor data. We have talked about the algorithms, the possible maze solving, but how do you control the motors? Simple motor control won't work out here, because of the main reason is that the motors needs to be kind of the control system of the entire robot has to be a closed loop control system. So by closed, I'm referring to that there must exist a feedback path from which will feed the input with the input of the output. Like here we are talking about the proportional integral derivative control system of the PID controller, which is a closed loop feedback control system for motion control, mainly actuators. So what happens is that we feed the control system with an input, let's say RT, then perform some operations on that control system using proportional, integral, and derivative, sum the entire sum of the three parameters, and then apply it to the planter process, and ultimately take a branch from the output again to the input RT. So it's a closed loop control system. We are feeding the input with the output, and the equation, there are three parameters, the KP, KI, and KP, KD, and KI. KI is an integral term, KP is a proportional term, and KD is a derivative term. So you need to handle these three terms The equation is also shown over here to like deal with the control system of the models. I will just show you a quick image or GIF which I got from Wikipedia. I think that will serve the purpose. See, initially the control system is extremely unstable. We keep on increasing the value of Kp, the proportional constant. And when the space, then we increase the value of Ki, which is the integral constant. You see that we obtain a kind of a sinusoidal graph. And then when you finally apply the Kd value, or we increase the Kd value, we obtain a fairly stable graph, or fairly stable system, to be specific. So what happens is that when a motor is being controlled by a PID controller, the main stuff that happens is that we need to control the speed of the motor, especially during the sharp turns. So to control the speed, we go for pulse width modulation in this technique, but to feed the pulse width modulation input with our desired input for control, we go for a closed loop feedback based control system, or the PID controller, which makes the movements of the motors pretty much stable across sharp turns. If you just search for a PID controller with the help of like PID controller based motors in YouTube, then you will see like how much stable it is. Now the concept of mesh solving and all those are over, so we move towards the concept of known and unknown environments. I will just stop in between to see whether I've encountered any question. So yes, we have to talk about the environments, because when you are dealing with autonomous robots, you need to map the environment, or you need to localize yourself in the environment, which might be known or which might be unknown. Now, tackling the navigation problem in known and unknown environments is totally different. And because in case of known environment, like take the example of the mesh solving. What we do initially we don't know the environment, right? We don't know what the mesh looks like. So we initially leave the robot to traverse across the entire maze. What it does, it records the entire maze and stores it in the form of a data structure. So the environment gets transferred from unknown to known, and then we tackle the navigation. But in cases of real-time systems like autonomous car, or like some kind of autonomous aerial unmanned aerial vehicle, or some any kind of unmanned vehicle, so you need to tackle the unknown environment, and sometimes it's not really possible for us to traverse the entire environment. That's totally not possible. You are certainly not going to leave a car and ask it to travel the entire globe. No, so that's not possible. Yes, we have certain parameters. Credit goes to Google in the form of Google Maps and Bing Maps. We do have the maps available to us, but the environment still remains unknown to us. Like what are surrounding features, lots of things stays unknown. So real time. Basically, when you design a robotic system, then you need to handle these cases of known and unknown environments in a different manner. I move forward, and we'll enter through the autonomous vehicles ecosystem. Now the things gets a bit more technical, because we're dealing with mapping, we're dealing with localization, we're dealing with control. The control part was already covered in the form of PID controller. The PID controller is the base controller for all autonomous cars. Now we'll be dealing with the mapping and localization. But before we deal with the mapping and localization, let's see, have a look over the stages of autonomous car. So in case of autonomous car, there are mainly total of 6 stages, starting from 0 and ending with 5. So all the normal cars we see on the road, especially in a country like India. So what happens is that, like, we don't have full automation. To leave aside full automation, we don't have any kind of automation, leaving aside some driving assistance. So automation level 0 refers to the normal cars which you see on the road, which doesn't have any kind of automation. It's totally under the control of driver, and there are no driver assistance. Now we enter the automation level of 1. So automation level of 1, This is like the entry level case of autonomous or self-driving car. So what happens is that in case of automation level 1, the driver gets assisted by some techniques like adaptive cruise control and some features like like steering, maneuvering, like left or right, and acceleration and braking can be controlled by the assistants. I mean, by the computer. So what happens is that the steering, either the steering or the acceleration and braking can be handled by the system. It's not like both the stuffs can be handled by the system at a single moment of time. That has to be handled by the driver. Suppose the computer or the system is dealing with the acceleration and braking, then the driver needs to handle the steering. That is a case of adaptive cruise control. I will come across this point later upon this slide where I have a detailed explanation for ACC. That's the first stage of automation. The second stage of automation is that the steering, the acceleration, the braking, both of these stuff can be controlled by the system, and the human driver needs to be kind of stay alert to some interrupts. That's the second level of automation. Second level of automation will also be attained successfully by Tesla, by Google self-driving cars, and some other companies too. Now comes the stage of total autonomy. That is automation level 3, a conditional automation. Now, in this case, the driver mode involves majority of the basic as well as advanced control. Now, so what happens is that in case of like advanced control or advanced automation of a self-driving car, there are three factors. The first is the steering, acceleration, and braking. Everything will be controlled by the system. The second thing that comes to the picture is the monitoring of the driving environment. Yes, we are talking about unknown environment. So there are radars that are fitted into the self-driving cars. There are lidars, there are radars, there are cameras which monitor the environment and kind of alerts the driver if something is happening. The driver has to be kind of alert all the time to see whether the system is able to handle or not. That's the third stage of automation. And the fourth stage of automation is a high-end automation where the driver have a very like a very low-level controls are with the driver, and all controls lie with the system or the CPU of the self-driving car. So in this case, what happens is that the driving mode, like steering, acceleration, braking, is also controlled. The driving environment and monitoring is also controlled. Add some advanced features like lane shifting, automatic parking, all this comes into picture. So like automatic parallel parking, then sometimes the case of overtaking a vehicle by shifting of lanes, that comes to the fourth stage of automation. Now the fifth stage of automation is what we actually desire, of what Google is actually targeting, the Google self-driving cars. So in the case of fifth automation level, it's totally autonomous with no human intervention. That means you sit in a car, there won't be any steering, there won't be any gas pedal, there won't be any brakes. What you'll have, you'll just have a tablet kind of display where you just enter destination and your car will take you to that destination. That's how the fifth stage of automation fully functions. It's a total case of full automation. We are still yet to attain that automation level as of now. Let's have a look at the basic architecture of any self-driving car. Now, this basic architecture remains constant across each and every self-driving car across all the ranges of automation, starting from 0 to 5. So, in the sensors unit, we have lidars, radars, camera, GPS, and encoders. I have talked about the wheel encoder. So, wheel encoder is nothing but like a kind of odometry data, which returns us a distance the car has traveled. Then we come across the GPS, the global positioning system, which provides accurate positioning system for the car up to like accurate up to a certain few meters. Then we have a camera, which helps us to detect traffic signs, signals, some foreign objects on the road. Then comes a concept of radar. So this radar provides us a 360-degree vision for the entire self-driving car. Radars are fitted at each side of the car. And then comes the concept of lidars. So LIDAR actually stands for laser detection and ranging. So what happens is like if I've just seen any, probably I have in. I will show you the architecture. The diagram. So in case of a LIDAR, it there is a sensor, transmitter come receiver at the top of the car, which rotates very fast, something like 70 times per second, and maps the entire environment. So that comes under the concept of LIDAR. LIDAR is also providing LIDAR is mainly used for localization and mapping. I will go with all the units a bit later on. Then we have the electrical control unit, or the ECU, which initially pre-processes the data, that is filtering the data, applying some kind of transformation like a Fourier transform or a Z transform, then processing the data to extract the features from the data set, and not the Excel data set, extract the features from the data that you are getting, and then there will be some kind of a decision making or rule engine that will be inside the electrical control unit, and then you will be having a user interface, which is totally dependent on the user, like where it needs to go, where you need to go, and all the steps. Next comes the concept of actuators. So in actuators, basically refers to any kind of movable object in a car, like the braking, the acceleration, de-acceleration, that is the gas pedal, the steering, and some other miscellaneous control like gear shifting, something like a wiper, and all the stuffs, like anything which is movable can be referred to as actuators. So that is the basic architecture of a self-driving car. Sensors provide data to electrical control unit, and the ECU then processes the data and sends the rule engine. After processing the rule engines, it sends the control signals to the actuators, and then the actuators executes that kind of action. So let's just have a look at the hardware stack, and we'll discuss this in detail right now. Radar. So initially, we have a radar, LIDAR, optics. Optics is mainly for providing the imaging perspective of the car. There's written traffic signs, signals, GPS, well encoders, and well encoders I also already mentioned is about the odometry data, and the processors, that is electrical control unit. Let's see the sensors role in detail as of now. So I have already created a source of the image. It's a Uber self-driving car which is being tested in some university campus. So I think it's in St. Petersburg. It's being tested. I'm not sure about that data. Anyway, so what are the sensors' role in case of a self-driving car? So basically, the radars are mainly for obstacle coverage and a 360-degree field of vision for the car. So there are radars that are fitted in the front side of the car, radars on the side of the car, on the back side, and all the sides. It provides a complete 360-degree vision, and there are no blind spots. Virtually, there are no blind spots in the car. So it's kind of you can do anything which is coming in your way. Then there's LIDAR, which is meant for mapping and localization. I'm keeping talking about the term localization and mapping. You will see what I'm referring to those in some moment of time. Then we have GPS of precision and localization. Again, the localization terms come to the picture. Mainly in simple terms, it's just a positioning, like to determine the exact position of the car. Wheel encoders for odometry. And then finally, we have the wheel mounted resonance sensor for close object detection. And this is like an insurance policy if any radar fails. Then we have the forward-facing camera for detecting objects on the road, traffic signs, etc. So this is the overall sensors role in case of self-driving car. We'll move forward to mapping the environment. So let's consider the world of robot to be represented as a two-dimensional matrix. So R represents the position of the robot, and the white, or shall I say like a lighter gray boxes show that nothing is present in those areas or those blocks, and the darker gray or more, the color which is more aligned towards black shows us the presence of objects. So what happens in this case, like we scan the entire environment of the robot, keeping R at the center. This type of grid or this type of map is usually referred to as an occupancy grid or occupancy matrix. Occupancy. So what happens is like we scan the entire environment and I'll just show the algorithm. Like we think of our environment as a 2D matrix, fill up the entire matrix with 0. Now replace that 0 with 1 wherever there's any object present. So that's how the entire mapping thing functions. It's just an extremely simple representation of the mapping algorithm that's normally being used in all kinds of self-driving cars. I'll just move forward with localization. So mapping and localization has to go side by side. So what happens in case of localization is that this hold on. Cool. Okay, so in case of localization, what we want to know is that where exactly the robot is present in an environment. We have seen in the map that the robot is present in R, and based on that R point, we have plotted the entire map. Now, localization, what it does, it gives us an exact, not the exact, the best probable exact location of the robot in an environment. Now, in case of localization, we combine data from each and every senses possible, starting from GPS to LiDAR to radar to ultrasound to camera. Each and every data is fused together to give us the most probable result, like where the robot is exactly present. Not exactly most probable result, I will say, because in robotics nothing is exact. Everything is just a probability. You will see in some time. So knowing a robot where you are is a case of the robot. Finding the best possible position of a robot in an environment using probabilistic methods. So we apply different probabilistic relations, some probabilistic distribution to find out the best position of the robot. Combine data from different senses to get a position estimate, or sometimes it referred to as a POS estimate or pose estimate. So that is what we call as localization. Now remember one thing, GPS cannot provide us the exact localization. GPS can provide us only to some accuracy, some few fits of accuracy. Only localization can be provided after combining multiple sensor data, which we come, this slide is about the position estimate. Let's consider a map. I mean, just a simple linear map. We have a robot R, we have A, B, C, which are three distinctive features of of the map or of the environment. Now we have programmed the robot in such a way such that if it detects either A, B, or C, it will return some kind of value. Let us assume that value to be 1. So what happens initially when the robot is in position of void, we get a value of 0. Then when it comes corresponding to A, we get 1. Similarly, B, 1, C, 1, and R, blank again 0. So it might appear confusing, a bit confusing now, but what actually is happening is that robot is believed, or robot is being believed that when the robot is present initially, it doesn't detect anything, and thus it returns 0. But whenever it detects some kind of features, now these features can be anything. Let's say it is just another car. So when a robot detects another car, it returns 1. That's how we determine the kind of estimate position of the robot, or we can just refer to as a position estimate. Let's take another very simple example where we have a robot in a room and there are multiple doors. Now the robot goes from one door to another door. In between two doors, there are spaces. So when the robot reaches one door, we get some kind of value. When the robot doesn't reach any door, or when it's between two doors, it doesn't get any value. So that's how the position estimate occurs. Now there are lots of positioning sensors. The initial measurement unit, or the IMU sensor, which returns the acceleration, the angular rate, sometimes a magnetic field, gyroscopes, and magnetic compass. This IMU unit, plays a very important role when there is no GPS signal, as in the case of tunnels, inside buildings, etc. Then we come across a GPS. So what the GPS does is like it provides us a lat and long of the robot or the vehicle, which helps us to get a very perfect or very good position estimate of the of the robot. Then we have odometers, which provides us a distance traveled by a specific vehicle. And then we have range finders, which provides the distance of the targets, with the sensor being the epicenter, like the lidar, the radar, infrared emitters, ultrasonic, and all those comes into the case of range finders. So those are some of the position sensors. We combine all this data to get a position estimate. So then there comes another concept, position uncertainty, because I mentioned it's all about probability. Sensors provide data, but not all data are 100% accurate. So to deal with any kind of inaccuracy, probability distribution studies, as in the case of this. So what happens is like, this is a real-time example position estimate. I have shown this image before, where I have just mentioned as 1. However, in real time, we don't deal with natural numbers, we deal with a probability distribution. Like if a robot doesn't sense anything, it returns 0. And if a robot senses anything, it returns a probable value or a normalized value, you can say. So if you just sum up the position of each and every case, which is 0 plus 0.33 plus 0.33 plus 0.33 plus 0, it will give you the probability which is equals to 1 or almost equals to 1. Since you're using 3, it's not perfectly divisible. So that's the case. Here I have got one question. Is the localization? What is the reference of localization for the bot? Well, that's a pretty good question. So what happens is that let's begin the slideshow over here. So the so if you're developing a bot and the bot has to navigate autonomously from one point to other point, then you don't know where the bot is exactly located. So in that case, the localization comes to the picture, because you need to understand where the robot is actually located. And to understand the location of the robot, you need to deal with the localization problem. Next comes the concept of SLAM, or simultaneous localization and mapping. So this is the last topic that I'll be dealing today, since I am shortage of time probably. So in SLAM, what happens is like we deal with the localization problem and the mapping problem simultaneously. It's a kind of a hard problem to solve, and lots of research are being carried out to solve this problem. So in case of SLAM, we estimate the position of the robot and map the environment at the same time. So you are at a position, you are mapping the environment. It's something like a good position estimate is required for mapping, obviously, and a good map is needed for localization. It's something which is mutually inclusive to each other, and both cannot exist without each other, and both has to occur at the same time, which is actually hard to handle. And that's where the concept of SLAM comes to the picture. There are lots of types of like you can have full SLAM, half SLAM, hectare SLAM. There are many types of SLAM that are available, and there are lots of algorithms that people have worked on. So that's the concept of simultaneous localization and mapping. Like you get to know your position and you get to do your map both at the same time, and that's the base, like the total base level architecture, base level design of all autonomous self-driving car. So to handle the autonomous self-driving car, you need to handle the problem of SLAM first. That's the base level problem you need to solve. The SLAM application is being used in multiple areas, including indoor, outdoor, underwater aerial vehicles, home, autonomous vacuum cleaner, and autonomous lawn mower. It might not be available in India, but it's available in outside. I've seen personally back in Bangalore, some company, I don't remember the name, they have developed an autonomous vacuum cleaner, which is pretty much good. Then in air, we have unmanned aerial vehicles for surveillance, autonomous drones, which like the Amazon delivery system. So that's the case of SLAM application. It maps as well as localizes itself in that map. Then in case of underwater, we have the case of reef monitoring. And in space, by reef monitoring, I'm referring to any kind of submersible unmanned autonomous vehicle which performs SLAM to localizes itself along the environment. Now, SLAM may like there are exactly kind of two possibilities. SLAM may be used both in manual robots as well as in autonomous robot. So what happens is that like suppose you're having a manual robot, let's say manual submersible underwater vehicle, which is being sent for reef monitoring. I need to map the entire reef. So in that case, SLAM comes to the picture. However, it's not an autonomous robot. So you're handling the SLAM problem is a manual robot. In space, well, I don't have to say anything in this because space is all about unknown environment. So whenever there's a concept of unknown environment and whenever there's a concept of localization, SLAM comes into the picture. For commercial, We have autonomous and self-driving cars, and there's one more point that I missed out in the slide, but I would like to talk about is like 3D mapping of archaeological buildings. Yes, this is a very kind of important, or I will not say important, kind of interesting topic, where SLAM is being used constantly to perform a 3D scan or 3D map of the entire archaeological building to to find some structural integrity and other mechanical, other civil stuffs. So that's one of the areas where SLAM is being used. Yes, that's the case of adaptive cruise control. Adaptive cruise control was first introduced by Bosch, Robert Bosch company. So it uses radar to detect object or cars in front. Now, based on the parameters, now see, I will just mention adaptive cruise control doesn't involve the capability of handling your car in lanes. Adaptive cruise control will just give you the autonomous nature in just acceleration, deceleration. It doesn't automate your steering wheel. So to automate the steering wheel, then you need to shift to level 2 automation, as I already mentioned. Adaptive cruise control is just level 1 automation, and it's being widely used in the market. So the main sensor involved in adaptive cruise control is a radar. It based on the parameters, the acceleration, deceleration is adjusted, and various slope control system is responsible for accomplishing tasks, as in like for acceleration and deceleration. So this closed loop control system is again refers to the PID controller, which I discussed earlier. I'll just have a quick discussion of my project out here. So this is a robot that I have developed back in 2016, probably. So what this robot does is like, it is based on the Arduino platform, and it has only 3 ultrasonic sensors. So these 3 ultrasonic sensors is virtually responsible for the entire mapping, as well as for localizing the robot in a specific environment. Please note the fact I didn't use any kind of GPS. I just used an odometry data. That also odometry data was simulated. I have just used this ultrasonic sensors, and I have used a magnetometer to determine the heading of the robot. So it consists of 2D occupancy grid at a specific instant of time, and then it implements the DFS for traversing, and then ultimately uses the distance algorithm for finding the shortest path. In the next, the links are given. I will share the link in the chat box. I have already published a paper regarding this project at IEEE, and also a DevMesh project at devmesh.intel.com. I'll share the link. This is a UI which I have designed. It's based on .NET, WPF framework. So what it does is like the heading is being displayed, like where the robot is facing. The heading is being displayed. Once you click on start, this is a kind of a schematic for the robot. These are 3 ultrasonic sensors. The red means something is zero, and green means well, you are clear to go. You have the connection pane. So this is the entire UI which I have made for this for the control, or I will say rather for monitoring this autonomous robot. So during the testing phase, I have used this map. It's just a kind of very simple map. This map was mapped into the picture which you can see above. So this is the most basic case of simultaneous localization and mapping. So this is the most basic use case you can say, and it's the most raw form, because I haven't used any kind of technically high-level sensor. I've just used simple ultrasonic sensor with some basic amount of filtering, and I was able to obtain a kind of better results, I will say, considering the fact of the sensors as well as the filtering techniques used. The architecture is pretty much simple. We have 3 ultrasonic sensors feeding the data to Arduino Leonardo. From there, I'm processing the data and sending it to the motor driver. I also have a digital compass which is sending the data to Arduino Leonardo, and ultimately the Arduino is interacting with the app using a RF receiver and transmitter. So that's about the entire process. You can have the resources from here. Probably I'm having a video also. And yes, that's all about. And if you want to have just study about robotics, like the localization problem, the SLAM problem, and also the Kalman filter, the extended Kalman filter, and there are lots of other stuffs in autonomous robotics, or rather I should say self-driving cars. So yeah, I will suggest this Udacity course. which is CS373. This course is perfect for beginners to get started with autonomous robotics. Thank you very much, and currently I'm totally open to questions. Wheels with encoders is quite very useful. We can use, yes, wheels are definitely useful because I mean encoders, because you need to you need to calculate the distance traveled. Okay, in localization, what is the reference of localization for the bot? Are you referring to like this? I'm just asking to Rishabh, like, are you referring to indoor environment or outdoor environment? If you are referring to indoor environment, then for the bot to travel, to navigate itself in an indoor environment, what you need to do is you need to kind of like you need to know where exactly your robot is located in an indoor environment. Let's consider the room, which is at the back side of this chair. Now we need to find out where exactly I'm located, right? By the vision, I can obviously say, but you need to attain the same thing by a robot. So, and that is how. So localization is obviously important in indoor environment. That is in the case of bots. Now, if you're talking about outdoor environment, well, I don't have to say anything because if you're going outdoors, localization is extremely important. So yes, I think Grace will upload this. I mean, the PPT, the code, the links will all be available at software.intel.com. I think you can just have a look from there. So thank you again very much for listening to this webinar. I hope you like this webinar. Thank you again. And yes, this video will be shared. Thank you very much.